In the last video, we were introduced to the idea of a differential equation. In this video, we're going to talk about what to do with one. So, what we're going to find is called the solution to a differential equation. And just like when we've solved equations throughout all of algebra, we found the values of missing variables. It's a little bit different here because we've got two different variables, and we're not going to find the values of any of these variables. What we're going to do is find the equation whose derivative is the given rate of change. Remember that the idea of a differential equation is we are given the derivative or the rate of change of one variable in respect to another. And so what we're going to find is the equation whose derivative is that rate of change. You'll see what I mean in just a second. Here's the example. A very, very classic differential equation, a population problem. The population of a little town, we'll call it Scorpion Gulch, is now 1,000 people. By the way, when we say now, this isn't so obvious, but what that means is when t equals 0, is 1,000 people. The population is presently growing at about 5% per year. Write a differential equation that expresses this fact, and we're going to solve it to find an equation that expresses the population as a function of time. So just like what we saw in the last examples, in the last video, we start with the variables and the differential equation. Don't even think about numbers quite yet. So what we're going to say first is the two variables that we have in this problem are the population of our little town of Scorpion Gulch and the time, which we're starting at time equals 0, but obviously that time is going to grow, and we're going to see how the population changes as time grows. Important to kind of identify in our heads that time is the x variable, the independent variable. The p, the population, is the y variable. And so when we're talking about the rate of change, it makes sense that we have dp dt. The population is growing at a rate, that's dp dt, the rate at which the population is growing, they tell us it's 5% per year. What we're going to do is translate that, just like we translated the last examples. This is a directly proportional example, meaning when they tell us the population is growing 5% per year, that means at any moment in time, the rate of change is 5% of the current population, 0.05p. And so this matches the two examples we had in the last case, where we had some constant of proportionality times the dependent variable, where the rate of change of a variable depends on itself, is a crazy idea. The rate of change of a variable depends on itself. Well, that's what's happening in this case too. The rate at which a town is growing depends on how big the town is. That's what percentage means. Okay. So now we'll talk about what to do, how we actually find the equation whose rate of change matches this. So I'm going to rewrite that same equation down here again. dp dt equals 0.05p, and we're going to follow these three steps: separate, integrate, solve. If you can remember those in a row, it's very helpful. Separate, integrate, solve. These are called separable differential equations. What that means by separable is we can separate the two variables. All of the p's on one side, all the t's on another. So that's what we're going to do. We're going to take the p and move it over to the left-hand side. We're going to take this dt and move it over to the right-hand side. We'll do that just by the same manipulation we always use on equations. We'll multiply both sides by dt. We'll divide both sides by p. And what we'll end up with is dp over p equals 0.05 dt. So we have separated the variables. That is a big deal. when we talk more about the AP scoring guides and how they work for this type of problem, you'll see how these are often 5-point parts to an FRQ. And if you don't do that first step, even if you do other things correctly, you're never going to get more than 1 out of those 5 points. So it makes a big, big, big deal to start with this separating. Okay. The next thing we're going to look to do is integrate. As we've seen, throughout all of algebra, if you want to get rid of something, you'll do its inverse, its opposite. So we've got dp and dt there. If we want to get rid of those things, we will integrate. Integrating both sides will get rid of both the dp and the dt. So let's actually do the integration. The integral of dp over p is the ln of the absolute value of p, and the integral of 0.05 dt is just 0.05 t. You might notice I'm missing something. I skipped something with that first integral. Of course, these are not definite integrals, so there is a constant of integration to worry about. But I only have to worry about it once, and that's why I'm only mentioning it here. Because if I had a plus c on this side and a plus c on the other side, they don't cancel out because they're not exactly the same constant. But I can move one constant over to the other side. And so what I'm going to do is just put both of them together on this side, plus c. And I'm going to put a little 1 here. I'm going to call it c1. It's hard to read right now. We'll fix that. The reason I'm calling it c1 right now is just because I'm not done solving. I'm going to do some manipulating and playing around, and that c1 might change into something else, and it's just helpful to keep track of them. So I'm going to call it c1 just for now, just meaning it's like this is my first constant. I might have other constants that come up later. You'll see. Okay, and then we're going to solve this equation same way we would solve it. Remember, what we're solving for is p because we want an equation where our independent variable is the sort of the variable you plug in to find the dependent variable, meaning we want to solve for our dependent variable. We want an equation with p by itself. That's what I'm going to do. I'm going to get p by itself. Well, right now it's inside of an ln, so I will exponentiate both sides. E to the ln of the absolute value of p is the absolute value of p. And e to the 0.05t plus c1. I can write that down now. E to the 0.05t plus c1. But I'm going to remind you of some of your old rules of exponents. When would you ever have an exponent with addition? Like, when would you have x to the 2 plus 3? Why would you ever see addition in an exponent? That would have come from having 2 powers multiplied by each other, x squared times x cubed. That would be x to the 2 plus 3, which means that we can similarly say that this e to the 0.05t plus c1, that could have come from e to the 0.05t times e to the c1. We're just using our laws of exponents to take that addition out of the exponent because I don't really want it there. One more step with this, I could say that e to the c1, because e is a constant and c1 is a constant, if I take e and raise it to the c1, it's going to be equal to some constant, which I don't know. So this is where the naming of the c's comes in. It's kind of silly to keep calling it e to the c1. It's just equal to some constant I don't know. I'm just going to call it c, or in this case I'll call it c2 because it's my second version. c2 times e to the 0.05t is equal to the absolute value of p. And again, the 2 there, it's just because it's my second constant. It's not necessarily equal to the first one, but it doesn't matter. Okay, and then p, it's the absolute value of p is equal to something. That means p by itself is either equal to the positive or the negative version of that. So I'm going to write that as p equals plus or minus c times e to the 0.05t. But that plus or minus is kind of a little bit silly because we're talking about population of a town that starts as a positive number And if it's growing, or really even if it's shrinking exponentially, it's never going to become a negative number. So that plus or minus C2 is really silly to call it that. It's going to be a positive number. And to be honest, even if we find out later in another situation that it would be a negative number, I can just call it another constant. Because positive C2, negative C2, whichever one it is, it's just some constant I don't know. So what I'm going to do is drop that plus or minus, and this is going to be my final constant, so I'm just going to call it C, e to the 0.05t. And this is what we call the general solution of the differential equation. I've gotten P in terms of in terms of T. I've written P, the population, in terms of the amount of time. Notice what kind of function it is. This is an exponential growth function, a e to the kt, as we learned about in Algebra 2. This is one of those times where it turns out you only ever knew half the truth. We talk about e in a lot of ways in Algebra 2. The truth is that this is really what e is all about. This is what e comes from. This is what it's for. E is the solution to a differential equation for proportional growth. That's really where e comes from. We don't have to worry too much about that, though. Okay. There's one catch to this, though. This idea of a general solution. It has a constant, an unknown constant in it, but don't we like to know what unknown constants are? Don't we try and find them? We saw this before when we used antiderivatives. Sometimes we used an initial condition to find out what C was. Well, we're going to do the same thing here. We're going to use an initial condition to find out what C is. So let's go back up to the problem and look and see what the initial condition was. They told us something. And the key is where they said that this population is now 1,000 people. I mentioned earlier that that meant now is when t is equal to 0. Well, that initial condition is at t equals 0, the population is equal to 1,000. So what we're going to do is plug that in. 1,000 equals c e to the 0.05 times 0. And if we plug in a specific t and p ordered pair, we can then find that constant. In this case, it's an easy example because e to the 0.05 times 0 is just 1. And so we get that 1,000 equals c. So this constant right here is equal to 1,000. And so we can write that down. P equals 1,000 e to the 0.05 t. And this is what we call the particular solution, where we've actually solved to find the constant. That's C. In our next example, we'll take a look at other differential equations that aren't necessarily related to E. But I want to highlight how important this one is. Because, again, I mentioned this a second ago, this idea of what E, as you know it, the continuous exponential growth, that's when we used E in Algebra 2. Where it comes from, this idea of continuous exponential growth, what that means is it's something that's growing at a constant rate of change, or sorry, a proportional rate of change.